Very good afternoon, everybody. This is Dr. Vaibhav Pandit, and today we are going to discuss the topic that is titled Ampere's Circuital Law. So, this is the topic from our subject Electromagnetic Field Theory, and already we have gone through various topics as we have the two parts here, electric field and the magnetic part. So, the Ampere Circuital Law belongs to the portion of the magnetic study here, the magnetic field study here we are going to have, and this is really very simplest law in this particular subject and the most important too here. So very first of all we shall see what is the statement of the Ampere Circuital Law, what information is conveyed by this particular law, and then we shall be solving few of the sample problems based on to this Ampere's Circuital Law. So here we take the title. And now, what is the statement of the Ampere Circuital Law? What information it is conveying us? So that we shall see. So the statement is Ampere Circuital Law states that the line integral of H about any closed path is exactly equal to the direct current enclosed by that path here. So the mathematical expression of this Ampere Circuital Law can also be given for this much of information. So it is here. So on the left hand side we see the closed integral h bar dot of dl, and that is equal to, on the right hand side it is expressed as capital I here. Now we get back to the problem statement, as here we are having the Ampere's Circuital Law for the study of steady magnetic field here. The measure of how much the magnetic field it is there in the previous live session I have already got it clear to you people. It is denoted by capital H. So capital H is nothing but the magnetic field intensity. It is a vector quantity. So here, as per the statement of the Ampere Circuital Law, the line integral of the magnetic field intensity about any closed path. So here we are having the integral is shown on the left hand side over the H here. Moreover, the path that is followed, that is a closed path here. So because of this much of information, here we are showing the closed line integral here. The closed integral, it means the starting point and the ending point of this integration process is the same. So this is what the thing that we have expressed on the left hand side of this mathematical expression here. Now as per this law here, this closed line integral of h bar is equal to the direct current enclosed by that particular path. So to explain the thing that is put forward by the Ampere here we take the help of one illustration. So in this illustration here we have the three paths here. Now first of all you see this is something kind of cylindrical rod that is carrying the current I as shown from the left hand side end towards the right hand side end here. So I is the total amount of current capital I flowing through this conductor body here. Now if we prefer the path A, so path A, this is the closed path. Anywhere you start and once you get back with the help of this particular path here, so you are at the same point here. So you can carry out the closed line integral of h bar dot of dl bar. So as per the Ampere Circuital Law, it is equal to the total amount of current I flowing through this particular conductive part that is inside the closed loop here. So now whatever the shape of the closed path is there, right now for part A loop here, it is of the circular shape. For part B loop, it is of the square shape here. But whatever it is there inside the loop, so it is the same. So for path B also, the same amount of current capital I is flowing here. So whether you carry out the closed line integral onto a circular path or a square shape path, it will be the same answer here. Now if you talk about the case of path C here, see the path C is not completely enclosing the conductor body that is carrying certain current here. Here you see the 2 points, when we join them and complete the closed path, see of course it is a closed path here, but it is carrying a part of the conductor having the total magnitude capital I for the flow of the current here. So when you are going to apply the Ampere circuital law for the path C here, so that time it will be of course less than that of the capital I here. So that will definitely depend on the physical dimensions of the conductor and how much portion it is lying inside the closed path denoted by C here. So this is what the brief information I have shared with you people regarding the concept behind the Ampere circuital law, and based on to this particular concept we are now going to solve few of the sample problems. I hope your all the doubts will get cleared and you will have the solid understanding of the Ampere circuital law and hands-on practice for performing the applications to the various situations. So here we go. We start with the first problem statement. Here it is. A hollow spherical conducting shell of the radius small a has filamentary conductions made at the top. Here it is denoted by r is equal to small a, theta is equal to 0, and the bottom, that is denoted by r is equal to small a, theta is equal to pi. The statement continues with another sentence where a direct current capital I flows down the upper filament, down the spherical surface and out the lower filament here. Now we are asked to find capital H in spherical coordinates. The two cases are provided here to determine the answer of H. The first one is inside and the second one is outside the sphere. Now if you focus the problem statement is completed here. You will see that there it is, the imagination of a spherical conducting shell here, a sphere here, and that is why it is quite convenient to make the use of spherical coordinate system for representation of the vector and other quantities here. So now first of all, what is the situation provided in this particular problem sentence that we are going to visualize with the help of one illustration that we are going to draw here. So as we have a hollow spherical conducting shell here and the radius a, it is mentioned r is equal to a, theta is equal to 0, theta is equal to pi. These are all the conditions that prefer the spherical coordinate system. So the spherical coordinate system is having the reference to be just the origin. Basically it is the point which is formed by the intersection of the three axes. Those are a part of the Cartesian or rectangular coordinate system here. So here if we have the vertically oriented z-axis perpendicular to the horizontally oriented y-axis, both are there in the plane of your digital screen, and the third axis, that is mutually perpendicular to the x and y, here it is. So in this particular plane of the digital screen we are showing it with the help of a tilted line here. So at the center there it is, the point origin formed at the intersection of the three axes. Those are mutually perpendicular here. So we just imagine one spherical surface that is centered at this particular origin, and as per this problem statement, here it is of the conductive material here that can flow a current through its body here. Now added information we use for this illustration from the problem statement, that to such a conducting sphere or the spherical shell here, the current is fed from the top here. So as we refer to the spherical coordinate system, we generally have the three coordinates denoted by r, then theta, and finally the phi here. So r is the radius of the sphere. Anywhere you can join the point on the surface of spherical shape to the origin, it will be simply r here. Theta is the angle made by this radius segment with the positive z-axis, that is the upwards direction here. So we have to measure it in downwards here. So when the point is on the positive z-axis here, so this theta will be equal to 0, and when the point is there on negative z-axis, as we complete the measurement of the angle like this here, so this is on the opposite direction, negative z, the angle will of course be of 180 degrees. that in radians we will be having pi radians here. The definition of the pi lies the same that we have learnt in cylindrical coordinate system here. Now we discuss the case here. So for the given information from the problem statement, we just feed the I amount of current from the top. So let us see, this current is flowing from top to down here. Now this will be flowing out through the surface area of the conducting sphere here like this, and it will be going out from the bottom end here. So this is what the connections as per the problem statement here. Now we are going to apply the Ampere circuital law to determine the amount of or the magnitude of the magnetic field intensity in the spherical coordinates inside and outside the sphere here. Just now we have learnt about or we have revised the statement of the Ampere circuital law, express it with the help of the mathematical representation as well as the illustration we have used it for the clarification here. Now if we consider any of a loop here or a closed path inside the circular body. Now you see, when I amount of current is flowing, see the flow of the current from any conducting body will be on its surface, not on its entire inside body here. If it is a hollow as mentioned from the problem statement, of course there it is not the question here. So there it is no current that will be enclosed inside this particular loop here. So here we are considering this particular loop that is centered on the z axis of course here, and as there it is no current enclosed, we shall conclude that for the part A of the problem statement here, h is equal to 0 when the radius denoted by r is less than small a here. So I suppose the part A answer is clear to you people. Now we go for determination of the magnetic field intensity that is outside the sphere. So outside the sphere, if you have consideration of any of the closed path, either you follow any random path having the starting and end point the same here, having the directions like this, or it may be of the circular shape or some other shape. So it will of course enclose the amount of the magnitude that is representing the current I flowing from top to bottom here. So as we apply the Ampere circuital law, it is of course enclosing the current I here, and as the situation is provided in this problem statement that a filamentary current is flowing from the top and then through the body of the spherical hollow spherical shape here, and then towards again the filamentary part on the bottom side here. The magnetic field intensity as per the Ampere circuit law, H will be equal to the complete current I. So it will be on the RHS negation of I divided by 2 pi rho a phi cap. A phi cap will give the direction here for the magnetic field intensity. So for determination of the direction of the magnetic field intensity, we have to always refer to the right hand screw rule or the right hand thumb rule. When the screw is there in the proceeding direction of the flow of the current here, in the way that we are having the rotation to it, so that is nothing but the direction of the magnetic field intensity, that is of course the a phi vector here. So as we substitute the value of the rho in terms of the spherical coordinates, because in the problem statement we are asked find h in spherical coordinates. Rho in the denominator is a parameter of the cylindrical coordinate system here. So this time what we are substituting, rho can be substituted by r multiplied to the sine theta here. So we get it to the form minus as it is I as it is in the numerator, in the denominator we write twice pi r sine theta multiplied to a phi here. So as this is the magnetic field intensity as per the SI units, we have to always represent the measurement in terms of amperes per meter. If it is the case of electric field intensity, of course we shall denote it in terms of volts per meter. So this was the answer for part B, where the case it was the loop is outside the sphere body here. That means R is greater than small a here. So this was our simple answer to the problem statement we have considered for this particular application of the Ampere circuital law. We have taken the two cases here, inside and outside the body of the spherical shape here, and of course inside the inside this particular loop or the sphere here, there it is no current, hence the answer will of course be equal to 0. H is equal to 0, that we have already mentioned here. So this thing you can outline as the answer for part A of the problem statement, and here this is the answer for part B here. So this you can outline here. So this completes our problem statement. I hope the things are pretty clear to you people. Now we shall go to have a practice of one more problem based on the Ampere's circuital law. So for the second problem, if we take the statement that is starting as an infinite filament on z-axis carries 20 pi milliamperes in the AZ direction. Three uniform cylindrical current sheets are also present, and those are provided with the magnitude of the current here expressed in terms of 400 milliamperes per meter at the location rho is equal to 1 centimeter. Then the second one, it is holding minus 250 milliampere per meter at rho is equal to 2 centimeter, and the third one minus 300 milliamperes per meter at rho is equal to 3 centimeter. Now we are asked to make calculation of the magnetic field intensity component H phi at rho is equal to, here we have rho is equal to 0.5, 1.5, 2.5 and 3.5. So this is what our problem statement is. As per the problem statement, we have to make the computation of the magnetic field intensity at the four places here. So this is our complete problem statement. I see a student Bikram Singh Bhattarai. Hello sir. Bikram, if you have any doubt, you can sure ask me. Now, what is the situation provided in this problem statement? I am going to elaborate with the help of one illustration you see. So, as you see here, there it is. First of all, the infinite length filamentary conductor that is all along the z-axis here. So, initially, I imagine the horizontally oriented y-axis, then again in the horizontal orientation the x-axis, both are perpendicular to each other, and the perpendicular direction to both of them, that is the z-axis here. So I have not shown the downwards arrow here. So red color you prefer, that this is for the flow of the current. So let us say for example some amount of current I is flowing in the upwards direction here. Now the amount of current that is flowing through this filamentary conductor, it is already cleared in the problem statement, that is of the 20 pi milliamperes here. So milli for 10 raised to the power minus 3 here. So this is one source of the magnetic field here. Whenever there it is the presence of a current, it produces magnetic field. Whenever there it is the existence of a static charge, it will produce the electric field here. So as per the problem statement, this is one source of the magnetic field here. Along with this filamentary current, there are three more current sources here in the various forms here. Here the shape it is mentioned to be of the uniform cylindrical shape here. On the surface of the cylindrical shape here, there it is supposed to have flow of current, and mentioned there it is the current density in terms of milliamperes per meter here. So there it is the first cylindrical sheet here carrying the current density 400 milliamperes per meter at rho is equal to 1 centimeter. As you see from the cylindrical coordinate system, rho is the radius of this cylindrical surface here. So let us imagine such a cylindrical surface here. The dark orange color that you see, that it is carrying the current on its cylindrical body here. So that magnitude in terms of the current density, it is mentioned 400 milliamperes per meter here. So the radius of this cylindrical shape, we can denote it as rho is equal to, here it is provided 1 centimeter here. So this is the second source of the magnetic field here. First is the filamentary current, second is the cylindrical surface here. Two more cylindrical surfaces are there with the increased radius of the cylindrical shape here. So another one, we imagine rho is equal to 2 centimeter, that carries the current expressed in terms of the density minus 250 milliamperes per meter here. So now as you compare this with the earlier, you will come to see that plus and minus sign is there. So of course the flow of the current in the second form of the current source here, there it is in the reverse direction as compared to the earlier one here. Now the last form of the current source here, we have another uniform cylindrical shape here that is carrying the current over its body. The magnitude it is expressed in terms of minus 300 milliamperes per meter at rho is equal to 3 centimeter. So with this illustration, I hope the complete situation behind this problem statement is clear to you people. So let us denote this much of radius by rho 1 for the first cylindrical surface, this much of radius as rho 2 for the second cylindrical surface, and this much of radius as rho 3 here. So rho 1 is equal to 1 centimeter, rho 2 is equal to 2 centimeters, and rho 3 is equal to 3 centimeters here. Now what we need to make compute? We have to make computation of H5 component. H is representing magnetic field intensity and the component should be in phi direction here. At the locations rho is equal to 0.5, rho is equal to 1.5, and rho is equal to 2.5, and rho is equal to 3.5. So when rho is equal to 0.5, it is inside all the three cylindrical surfaces here. When rho is equal to 1.5, it is inside the bigger two cylinders here, but outside the smallest cylinder here. When you have rho is equal to 2.5, it is somewhere here, that is inside the biggest cylinder but outside the two cylinders. And when rho is equal to 3.5 centimeter, so this particular point is outside all the cylindrical surfaces here. Now considering this much of information, we are going to make the computations here. So we find the magnetic field intensity H5 component at each of the required radius by applying the Ampere circuital law that just now we have revised here. So for that purpose, we are going to consider or imagine the circular path for this much of radius value here. So initially we consider rho 1 is equal to 0.5 centimeter here. Now the mathematically we can express the application of the Ampere circuital law as closed line integral h bar dot of dl bar, that is equal to 2 pi rho 1 into h phi 1 component here, that is nothing but equal to I suffix ENCL. So ENCL is just to express the enclosed current here. I is for of course the current, ENCL for the enclosed current here. Now you see here H phi is along the periphery of the circular loop here. So whenever there it is a current carrying conductor here, current in the upward direction, so that time thumb in the direction of the current, the curled fingers will give you the direction of the magnetic field intensity H here. So here what we have done, when the radius is denoted by rho 1 here, so 2 pi rho 1 will have the periphery of the circulating path here, and that it is multiplied by the H suffix phi 1 here, and according to the Ampere circuital law it is equal to the total amount of current flowing through that conductor here, I enclosed here. So for 0.5 here, so as it is only enclosing the filamentary conductor that is carrying the magnitude of current 20 pi milliamperes here, there it is no current component from the cylindrical shape current sheets here. Here only the filamentary conductor is enclosed here. That is why the magnitude here we put 20 pi milli, we substitute by 10 raised to the power minus 3 and express it in terms of the amperes here. Therefore, as we require the H phi component, as it is the first case, we denote it by H phi 1 here. So from the above expression, we can express it as 10 into 10 raised to the power minus 3 divided by rho 1 here. So 2 and pi we have to cancel out here, and this way we got this expression here. Now substituting the value of rho 1 is equal to 0.5 centimeters here. We have to get that converted in terms of meters to follow the SI standard units here. So when we substitute 10 into 10 raised to the power minus 3 divided by 0.5 into 10 raised to the power minus 2, we obtain here. So this calculation gives us the H phi component is equal to 2.0 amperes per meter here. Magnetic field intensity, always remember you have to express in terms of amperes per meter. When it is the case of electric field intensity, you always express it in terms of volts per meter here. So the first answer we are finished with here. You can outline the answer here. This is the required answer for part A. I can consider here. At rho is equal to 0.5, we have applied the Ampere circuital law and determined the H phi component here. Now we shall move on to determine the H phi component at rho is equal to 1.5 centimeter. So here we denote rho nothing but by rho 2 here, that is equal to 1.5 centimeters here. Now here again we have to enclose the current components inside the loop here. So as we have the closed path having the radius rho 2 denoted 1.5 centimeter, it is enclosing the filamentary conductor that is holding the magnitude of current 20 pi milliamperes in positive AC direction, and one cylindrical shape current sheet that is having the magnitude of current expressed in terms of 400 milliamperes per meter, and that is having the radius rho is equal to 1 centimeter. Why this is happening? Because rho 2 is equal to 1.5 centimeter is greater than that of the radius of the smallest cylindrical shape current component here. So the application of the Ampere circuital law takes the form where we write the expression 2 pi rho 2 into H phi 2 component, that is expressed as, for the filamentary current we have 20 into pi, and for the current that is associated with the cylindrical shaped current sheet here, that is equal to 2 pi multiplied by 10 raised to the power minus 2 into 400 here. So this is all in terms of milliamperes here. So this relation is having the only one unknown, that is H phi 2, which is required to be computed here. So this equation implies that H phi 2 is nothing but 10 plus 4.00 divided by 1.5 into 10 raised to the power minus 2 here. So the addition in the numerator and the division here gives us the required answer for H phi 2, that it is 933 into 10 raised to the power minus 3. So as this is magnetic field intensity, we have to express it in terms of ampere per meter. 10 raised to the power minus 3 we express in terms of milli. So H phi 2 becomes the required answer 933 milliamperes per meter here. So if you divide the problem in terms of four parts here, A, B, C and D. So for part A we have already found the solution. This is the solution for part B here. Now to get the answer tallied here, you can get back to the illustration that I have drawn. Cylinder inside the cylinder, and at the center there it is of course the filamentary current that is flowing the current in the positive AZ direction here. Now it comes for the third case where we have to make computation of the things at rho is equal to 2.5 centimeter here. So in the sequence we shall be denoting rho is equal to rho 3, that is holding the value that it is 2.5 centimeter here. And now as we just imagine one closed path having this much of radius, rho is equal to 2.5 centimeter, it will of course enclose the three current components here. The first one, that is centrally locating the filamentary current. The second one is the cylindrical shape, rho is equal to 1 centimeter. The third current component is of course again the cylindrical shape, that is having the radius rho is equal to 2 centimeters here. So the final expression for the magnetic field intensity component in phi direction, so that is denoted by H phi 3, is given as, we get it to the form 10 added by 4 minus 2 into 10 raised to the power minus 2 multiplied to 250. This is all divided by 2.5 into 10 raised to the power minus 2 here. So when we make the simplification to this expression, we get the answer for the magnetic field intensity component denoted by H phi 3, it is equal to 360 milliamperes per meter here. So this is the answer for part C, and then we have a focus on the last portion to solve. The similar procedure we have to follow here, that is at rho is equal to 3.5 centimeter. As already discussed, this particular point, if you consider at a distance 3.5 centimeter away from the z-axis and draw a closed path here. So this path is outside the body of all the cylindrical shape current components, of course the filamentary component also. So this will enclose all the four current carrying components. The first one, the filamentary component, the second, third and the fourth are of the cylindrical shape, given the corresponding the current densities here expressed in terms of amperes per meter here. Now here we get the details, and from the relation we get H phi 4 is equal to 10 plus 4 minus 5 minus 3 into 10 raised to the power minus 2 multiplied to 300. This is all divided by 3.5 into 10 raised to the power minus 2 here. So when we make the computation, it will lead to the answer 0 here. So the answer 0 is coming just because reversals of the directions of the current carried by the four current components here. As you get back to the problem statement, you will come to see that there it is the positive sign for the first current carrying component, the filamentary current on the z-axis here. So it is going towards the positive z-axis. For the second component also it is positive. It is expressed in terms of 400 milliamperes per meter. So it is also going towards the positive z side. Then for the third and the fourth component, there it is the mention of the negative sign, minus 250 milliampere per meter and minus 300 milliampere per meter. So because of the reversals of the signs here and the equality after making the computations here, this has got cancelled each other, and finally we are left with the H phi component to be equal to 0 here. So this is the answer for part 4. This is the answer for part 3 here. So this way we have the solution to all the four parts as per the problem statement requirement here. So this completes problem number 2 here. I hope the things are very much clear to you people, and now we are going to head towards the another problem that is also based on the Ampere's circuital law here. Now in this particular problem I am going to share you and also practice some additional parameters associated to the magnetic field here. So in this particular problem statement we will be provided with a new parameter that is quite known to you people, that is the conductivity here. So with the help of the information provided for the conductivity, we will be required to determine the value of the cross-sectional current density for the practically existing the volume current component here, that is usually expressed by the letter capital J here. We have to also make the computation of the total amount of current by using that information, and finally we have to apply the Ampere circuital law here. So for this particular purpose, we start with the problem statement. So it is, assume that there is a region with cylindrical symmetry in which the conductivity is given. Here we have sigma is equal to 1.5 e to the power minus 150 times rho, and the unit is Ks divided by m here, and an electric field of 30 A suffix Z volts per meter is present. So what is the problem statement? We have to find J in part A. We have to find the total current crossing the surface rho less than rho 0, Z is equal to 0 for all the values of the phi, and at last we have to make the use of Ampere's circuital law to determine the value of magnetic field intensity. So this is what the simplest question here. Now to see the short and simple information provided in this particular problem statement, we draw a simplest illustration here. So here we take the help of the vertically oriented z-axis, horizontally oriented y-axis, and the x-axis. So all are mutually perpendicular to each other, intersecting into the origin here. Now as the problem is, assume that there is a region with cylindrical symmetry having certain conductivity. So we imagine a cylindrical surface that is centered at the z-axis here. So here we have the cylindrical shape denoted here. So as per the problem statement, inside the body of this particular cylinder, the conductivity value sigma is different, and outside the body of this particular cylinder, the conductivity value is different here. See, the conductivity defines whether the given material is a conductor or not. Generally, for categorization of a certain material, we have the three parameters. First one is the conductivity denoted by the sigma. Another one is the permittivity of the medium denoted by the epsilon, and the third one is the mu that denotes the permeability of the material here. So here epsilon, the permittivity of the medium, for air or free space we denote it by epsilon 0. It is of course expressed in terms of farads per meter. So it is basically whether the given material is allowing the flow of electricity through it or not, electric field or not. So that is permittivity of the medium here, expressed in terms of farads per meter. Farad is basically the unit of the charge here. When we talk about the mu here, it is permeability of the medium, whether the magnetic component can cross the medium or not. That is basically expressed in terms of the mu here, and the value is expressed in terms of Henry per meter. Along with these two, I hope you are very much familiar with this epsilon and mu. Both are the constant values for the free space or air. So 8.854 into 10 raised to the power minus 12 you have used for epsilon, 4 into 10 raised to the power minus 7 you have used for mu 0 here. Here it is the third component, very important to define whether a material is conductor or non-conductor, that it is sigma. So in this problem statement, this sigma inside the body of the cylinder Here it is mentioned 1.5 into e to the power minus 150 times rho, mentioned in terms of kilo as per meter here, as for the Siemens here. Now, along with the existence of this conductivity, there it is the electric field of 30 Az here. So Az is upwards direction here. See, the electric field is there, that is having the direction upwards here, from bottom to the upwards here. 30 Az, the unit of measurement is volts per meter here. Now in the part A, we are required to make computation for J here. Now here what we shall do, we shall make the use of the relation that is giving us J in terms of sigma, the conductivity, and the electric field intensity. This is usually also referred to as the Ohm's law in the wireless medium. So this is J is equal to sigma E. What usually have the information regarding the Ohm's law? Ohm's law is relating the voltage to the current, and the constant of proportionality is the resistance here. So the reversal is the case here. Instead of the resistance, here we are referring the constant of proportionality by the conductivity. E expressed in terms of the volts per meter here, and J here it is expressed in terms of the amperes per meter square here. So amperes for J, volts for E. So this is of course the Ohm's law here. So as we are required the value of J here, we require the values of sigma and E. So both the values are provided in the problem statement. So we just put the values here, we get the expression of this form: 45 times e to the power minus 150 times rho Az here. So this is in terms of the kiloamperes per meter square here. So at whatever the point you require to find J here in this problem statement, it was not specified that at this much of point you make the computations here. So therefore we leave this expression as it is here. So J is equal to this RHS. This is what the required answer to the part A of this problem statement here. Now we shall move on to see the details to make the computations for getting the answer for part B here. So in the part B, we require to find out the total current crossing the surface rho less than rho 0, Z is equal to 0 for all the values of the phi. So to apply these particular things, the total current can also be determined by having the surface integral over the current density that just now we have find out as the answer for part A here. So this is what we have obtained here as the answer for part A. We are going to have integrated here, and the integration will be on 2 dimensions here. So here we express the total current I will be equal to the surface integral J bar dot of ds here. So J, as it is expressed in terms of ampere per meter square is for the square area here. So the area is defined by the 2 dimensions here, of course. So when you have the integration on both the dimensions here, it will of course give you the total amount of the current here. So I is equal to the surface integral J bar dot of ds bar. Now here we apply the limits to the integrals. The first is 0 to 2 pi for the integral that is associated with the changes into the angle phi here. Here it is associated with the d phi. The next limit is for 0 to rho 0, where we have the integration associated with rho into d rho here. No, rho is in multiplication to d phi here. Here it is the d rho, just the change along the radial direction in the cylindrical coordinate system here. And this is what the substitution we have carried out. In place of the j, we are associated with only the magnitude to determine first of all the I here. The directional information can later on be also added to this particular expression here. So just integrating, we have to apply the limits to the specific portion on the RHS here. So we keep 2 pi into 45 divided by 150 squared this ratio multiplied to e to the power minus 150 times rho to be the constant here. After solving one of the integral 0 to 2 pi, and inside the bracket we apply the limits 0 to rho 0, that is for the difference minus 150 rho minus 1 here. And of course this is the total current. The multiplicand is 10 raised to power 3 here, that we express in terms of kilo, and amperes is the SI unit here. So as we simplify the RHS, we get the form of the total required current, that is I is equal to 12.6 in multiplication to the square bracket that has 1 minus, in the bracket we have 1 plus 150 times rho 0. This bracket is multiplied to the exponential e to the power minus 150 times rho 0 here. So here it is expressed in terms of the amperes here. So this completes the answer to part B here. For the part A, it was required to make the computation of the conduction current density denoted by Ga here. This is the answer. And for part B, we were required to make the computation for the total amount of current. So total amount of current, here it is. So both the answers for part A and part B I have outlined. You can also outline the things here. Now we get to the last portion of this problem statement, that is the part C here. So in the part C, it was suggested to make the use of Ampere circuital law for determination of the magnetic field intensity here. Now as the things those have been conveyed from the given data of the problem statement, we have a symmetry in the cylindrical shape here, and this symmetry is suggesting that the circulating direction for the magnetic field intensity is of course there. So this magnetic field intensity component H will be only in the direction of the phi here. So we consider a circular or a closed path of integration that is centered on the perpendicular direction of the z axis here in the upright orientation here, and then the application of the Ampere's circuital law will lead to the equation. Here we write 2 pi rho into h pi is equal to I ENCL in the suffix here. So this is representing the enclosed current here, the current component that is enclosed inside the closed path. Here it is denoted here. And now we have the periphery denoted for the circular path by rho to be the radius here. Here it is 2 pi rho multiplied to the magnetic field intensity component here. So this is the expression coming by applying the Ampere circuital law here. So now for the I enclosed, we can make the substitution from the answer of the previous part, that is part B here. So there it was 12.6 in multiplication to the square bracket that has 1 minus, in the bracket 1 plus 150 rho 0 multiplied to the exponential e to the power minus 150 rho 0 here. So in this expression, rho 0 will be replaced by the variable simply rho here, and then we obtain the expression, the required expression we write for h pi, that is equal to 2 by rho in multiplication to the square bracket that has 1 minus, in the parenthesis 1 plus 150 times rho in multiplication to e to the power minus 150 times rho here. So as this is the magnetic field intensity component, so it is expressed in terms of amperes per meter here. So this is what the solution to part C here. Solution to part C here, and this way we are done with the problem 3 here. Now we go for solving the fourth problem, that is again based on the Ampere's circuital law here. So here we start with the problem statement. The problem statement is: a current filament on the z-axis carries a current of 7 milliamperes in the AZ direction, and the current sheets of 0.5 AZ in terms of amperes per meter, and the second one minus 0.2 AZ again in terms of amperes per meter, are located at rho is equal to 1 centimeter and rho is equal to 0.5 centimeter respectively. Calculate H at. So we have the four parts in the problem statement. For part A, we have to make the computations or the calculation of magnetic field intensity H at rho is equal to, we have 0.5 centimeters. In the part B, rho is equal to 1.5 centimeter. In the part C, rho is equal to 4 centimeter. And in the part B, we are required to answer the question, that it is what current sheet should be located at rho is equal to 4 centimeter so that H is equal to 0 for all rho greater than 4 centimeter here. So this is our problem statement here. So the short and simple problem statement, we get back to the given details of the problem statement here. So initially we find a current source here that is producing the magnetic field in the surrounding. That is a filamentary current along the z-axis. The magnitude of current is 7 milliamperes in the upwards direction along the positive, that is AZ direction here. Along with the first source of current, we have the second source of current, that is of the surface type here. So it is a current sheet. So this current sheet is having the cross-sectional current density expressed as, we have 0.5 AZ amperes per meter. There it is additional current sheet, that is 0.2 in negation AZ amperes per meter here, and these are respectively located at rho is equal to 1 centimeter, rho is equal to 0.5 centimeter. So this is the second component situated at, this is the third component situated at rho is equal to 0.5 centimeter here. So this way we have the total 3 current sources here that will be producing the magnetic field in the surroundings here. So the required calculations for magnetic field intensity will be the net result by consideration of the 3 here. First of all, we will like to answer for part A. So we have to make calculations for H provided rho is equal to 0.5 centimeter. So at this time I am not going to draw the diagram here. Diagram you have to draw on your own. So the thing is very simple. At the x-axis there it is the filamentary current, and then the two current sheets are there at the respective locations. Rho is equal to 1 centimeter, rho is equal to 0.5 centimeter, and here for the part A, rho is equal to 0.5 centimeter, we have to consider for calculation of magnetic field intensity component here. So what I do here, we are either just inside or just outside the first current sheet. So both will be calculating H for both of the cases. So for the just inside case of the current sheet here, we shall apply the Ampere circuital law to a circular path, a closed path here. That closed path will be centered on the z-axis. So this application of the Ampere circuital law will give us the mathematical expression where we have the circumference of the closed path denoted by 2 pi into rho multiplied to the magnetic field intensity component along the circumference direction, that is H phi component here, and that is equal to the total amount of the current enclosed. So the enclosed current component is a filamentary, that is at the exact center along the z-axis. So it is carrying 7 milliamperes of current, hence on the RHS we write that is 7 into 10 raised to the power minus 3 here. So this is the application of the Ampere circuital law just inside the current sheet here. So this expression employs to the form where we write H, that is just inside, expressed as the RHS, the previous one, that it was 7 into 10 raised to the power minus 3. This is all divided by 2 pi into, here we have 0.5 into 10 raised to the power minus 2. The direction, it is always a phi direction here, and the simplification gives it to be equal to 2.2 into 10 raised to the power minus 1 a phi, expressed in terms of amperes per meter here. So this was the case as rho is equal to the same location 0.5 centimeter. We have to tally both the conditions here. So this was for just inside the current component here. The second is just outside the current sheet, that is again at the location rho is equal to 0.5 centimeter here. The application of the Ampere circuital law will give you the expression. Here it is 2 pi rho h phi is equal to 7 into 10 raised to the power minus 3 minus, here we have the details from the current component here, that is minus 2 pi multiplied to 0.5 into 10 raised to the power minus 2 multiplied to 0.2 here. So this particular relation from the application of Ampere circuital law will give us the H component for the just outside condition, that is 7.2 into 10 raised to the power minus 4 divided by 2 pi into 0.5 times 10 raised to the power minus 2 into the a phi direction here. Finally, simplifying it to the form 2.3 multiplied by 10 raised to the power minus 2 a phi component, expressed in terms of amperes per meter here. So this is what the solution, the two solutions we have found out for the part A here, because the thing had just two sides here, that is why both the things have to be considered. This is the H just inside, this is the just outside, considering both the cases while applying the Ampere circuital law here. Now we shall go to have computation for again the magnetic field intensity component H at the consideration of rho is equal to 1.5 centimeter here. So now all the three current components will be enclosed when we have the consideration rho is equal to 1.5 centimeters, because you see the filamentary conductor at the center, it is of course on the z axis, then the second and the third current components are at rho is equal to 1 centimeter, rho is equal to 1.5 centimeter. This distance rho is equal to 1.5 centimeter is greater than that. That is why all the three current components will be enclosed, and the application of the Ampere circuital law will give us the expression 2 pi multiplied to the parenthesis where we have 1.5 into 10 raised to the power minus 2 times h phi here. So this is equal to, from the filamentary current 7 into 10 raised to the power minus 3, we subtract 6.2 into 10 raised to the power minus 3, and then for the third part we add 2 pi into 10 raised to the power minus 2 multiplied to 0.5 here. So this expression is having only one unknown on the left hand side, that is h phi component. So this is the h component at rho is equal to 1.5. The simplification will be to 3.4 multiplied to 10 raised to the power minus 1 a phi component. So this we have to express in terms of amperes per meter here. So this is what the solution we have as the answer to part B. Now after this solution we have to focus for determining the answer for part C here. So for part C we have a consideration at, we require rho is equal to 4 centimeter here. So here the Ampere's law, as just now we have applied to determine the answer of part B here, we have to replace rho is equal to 1.5 centimeter with just rho is equal to 4 centimeter on the left hand side here. So this corresponding change will lead to the answer of the form, that is h phi component, that is at rho is equal to 4 centimeters, we obtain to 1.3 into 10 raised to the power minus 1 into a phi, the unit vector showing the direction of the magnetic field intensity, and this intensity vector is expressed in terms of amperes per meter here. The same procedure we have to follow for determination of answer of the part B and that of the part C here. So the repetition of the process for the change into one of the parameter will definitely practice you a lot to understand the thing here. Now we come to see the last part here. So the last part, the question is, what current sheet should be located at rho is equal to 4 centimeters so that H is equal to 0 for all rho greater than 4 centimeter. So here the condition is put that the H has to be equal to 0 here when we add one more current component here. So to do so, the effect to have this H is equal to 0, we require the current in the reverse direction here. So here we require that the total enclosed current to be equal to 0 so that the net current in the proposed cylinder at 4 centimeter must be negative the right hand side of the first equation that we have seen while solving for part B here. So that component, it was minus 3.2 into 10 raised to power minus 2 here. So that time surface current density at the 4 centimeter will be the equation for this criteria we just formed. K is equal to minus 3.2 into 10 raised to power minus 2 divided by 2 pi in multiplication to the bracket that has 4 into 10 raised to power minus 2, and this ratio is multiplied by Az here. So this is the direction of the cross sectional current density for the surface current here. So this simplification leads to the form of K is equal to minus 1.3 into 10 raised to power minus 1 Az. This is in terms of amperes per meter here. So this is the required answer as a solution to part D here. So this way we are completed to solve part A, B, C and D also for the fourth problem statement here. So in this session we have addressed the statement of the Ampere circuital law, the mathematical expression to describe what is stated in the Ampere circuital law we have discussed. We have also taken the help of the illustration to describe the same. The understanding, I hope it is quite simple, and the application of the Ampere circuital law requires a little bit of imagination. So accordingly it will be quite helpful for the student if you draw the illustration by considering the various references that you have learnt while we discuss the coordinate systems here. Either you select the rectangular coordinate system, cylindrical coordinate system, or the third one, spherical coordinate system, as per the requirement. So I hope the things are clear for the topic Ampere's circuital law here. We shall meet by the next week with another topic from our subject. That subject will be again the electromagnetic field theory, and the topic will be the Stokes theorem in magnetic field. See, the Stokes theorem you will understand if you have solid understanding of the Ampere's circuital law. It is what the same thing that the divergence theorem is depending on the understanding of what you have learned in the Gauss's law for the electrostatic part. For the steady magnetic field, here it is the pair that the Stokes theorem is depending on the understanding on the Ampere's circuital law. Only the thing is you have to practice a lot mathematically. Finding out the derivatives or the integrals will be a need there, so that you practice. Rest of the things are very simple here. So